Hello everyone. I'm going to present my understanding of a blog post about superposition in neural networks. It was actually covered by you in February. So I got interested in and decided to kind of try to expand it to cover what we have time to do. And to begin with, let's not give definitions and rather cryptic stuff in the beginning, but start with considering a toy example, toy problem. In this toy problem, let's say we have a data set of faces, 4-dimensional faces. Comprised of an eye, a nose, a lips, and cat's eyes. So let's say we want to project this 4-dimensional head into 2 dimensions in a way that we can reconstruct the original face from the 2-dimensional representation. And let's also assume that we want to reconstruct this face in a way that we actually care more about reconstructing eye and nose more accurately than we want to reconstruct anything else. In this case, we can write a loss function like that. It's basically a quadratic deviation from the true feature times the importance of this feature. Since we are more interested in eye and nose, we give more importance to them and less importance to everything else. And let's think what it might look like, what this squeezed representation might look like in 2 dimensions. So, since eye and nose are more important, we might assume that a model that aims at minimizing the loss will just project the eye and nose features as they are and kind of ignore the rest. This way we squeezed 4-dimensional face into 2 dimensions. So why can't we also project the lips and head features into this space? Well, firstly, because they are less important and they do not affect the loss function as much as other features. Second, we actually don't have enough dimensions in 2 dimensions. We squeeze 4 dimensions into it, so lost. If we actually try to do that, we will see that those reconstructed or less important features will interfere with more important features in the reconstructed picture. So that's it. However, what if we consider the same problem, but now our facial features can be sparse. So some faces need nose, eye, head, or whatever. And we actually vary the extent of sparsity, so that sometimes actually usually we have only one feature, non-zero feature. In this case, let's consider the example. So when airline companies are selling tickets to flight, they are actually selling more tickets than there are places in the plane. That's because they assume that not everyone will actually come to the flight, and they will be able to both maximize the income and actually carry all the passengers that come to the flight. I guess we can assume that if we can extrapolate this reasoning into our problem, if the features are sparse, a good model that aims at minimizing the loss will try to squeeze all 4 features into 2 dimensions. But since there are not enough dimensions to actually squeeze them all without interference, a good model tries to put them into a superposition. So in superposition, features are actually interfering with each other. They have non-zero dot product with each other, but a good model, good non-linear model, that's important, can actually reconstruct this superposition state into a proper phase. More or less clear. So that's what superposition is, when a model manages to squeeze more features into less dimensions than there are features. This can happen in many ways. The case we consider here is relatively simple, but if there are more features and the model tries to actually represent them all, they might start to look like 5 beam stars inside that. Okay. We kind of got an idea and intuition what superposition is. What if we want to develop a tool for actually quantifying, assessing this superposition? What can I do? So on the same example with spatial features, let's see how aberration that manages to squeeze them all into dimensions can look like. So if in this case the regional features are 4-dimensional vectors and superposition representations are 2-dimensional vectors, an operation that projects 4-dimensional features into 2 dimensions look like this. And an inverse separation looks like this. Do you have an intuition why nonlinear models cannot actually project those 2-dimensional features back into 4 dimensions without loss?
What? There would have to be, I mean, like, the information had to be distributed across multiple places, but
Well, I
This
guess
is the SPD.
SPD.
If you have a rank, and then if you have d dimensions, which is smaller than n.
Yeah, but it would not be able to project them back perfectly.
Right, because of,
But if we add non-linearity in this case, really function, then we can actually, if we want, we can make kind of calculations by hand. But anyway, we establish what projecting function may look like. What can we do with it? First, we can visualize this kind of matrix, see what it looks like. Second, we might come up with some measures of superposition. One of them might be kind of a measure of how many, given a feature, how many other features are overlapping with it. That's the idea of this measure. And another thing is we might want to try to calculate kind of dimensions reserved for an original feature.
it's 2 just a correlation matrix, basically. Covariance matrix.
Oh, it's actually a scalar.
Oh, okay, that one.
So on the example we considered, we want to do that actually very simply. So this stage matrix looks like this. We can color code it into colors and get a more visual representation of that. As for other measures, you can see that a measure of superposition, this the product, sum of the products for each feature is 1, and dimensions per original feature is 1/2. 1, just half. Okay. What does it mean? From this picture, we can see that what this 1. It means that whatever vector we are taking, we can see that it is actually interfering with some other vector. And in this case, the measure of this interference is 1. As for this number, we can see that for each image, again, for each feature representation, we can see that it is sharing the dimension with some other feature in a kind of equivalent form way. So they're each sharing 1/2 of hidden dimension.
Seems like you would have to have bounds on the weights, the magnitude of the weights to have these properties ever occur.
In this case, we are assuming that the features, the vectors lengths are 1, but those equations, original expression for those measures actually include this hat. It is a normalized vector. So okay, we got an idea what superposition is and how we can quantify it. Let's actually get to the content of this blog post. So in this post, authors are analyzing how superpositions may look like what structures hidden vectors can form, how they behave, and that kind of things. So let's move to how superpositions can look like. This case was fairly simple. It's just superposition is diagonal, but if we had, say, 4 features, not 4 features, but 3 features, the superposition might look like this. Triangle. So to consider a more general case, let's consider the next problem, another third problem, which is considered in this post. So given some vector of features in n dimensions, let's try to project it into lower dimension and then reconstruct it. It's fairly familiar. It's fairly actually quite the same as what I told before. So features can be 0 with probability S, which is a measure of sparsity, or otherwise they are uniformly distributed on 0 to 1. And features have assigned importance that affects the loss function. The more important the feature is, the more the error of reconstructing this feature affects the loss. And let's define the models we will be using. So it's kind of a, I guess, 2-dimensional. No, it's not going to be. It's kind of an autoencoder. In the first case, it's just linear autoencoder or PCA. In the second case, it's slightly non-linear autoencoder. Oh, okay. So the authors of this post might run a simulation, run a training. They considered 20 original features. The original feature space to be 20-dimensional and the hidden space to be 5-dimensional. And they assigned an importance, the explanation became vague. So first feature importance is 0.57, then is the square root and so on. And let's look what they got. So for linear models, they can see that the linear model is encoding only the most important features. It is not able to encode any superposition. Okay. As for nonlinear models, the reconstruction, the hidden dimension starts to depend on the sparsity of the data. So if the data is perfectly dense, the solution looks like the linear model. But as we start to increase the sparsity, we start to see that our models start to encode less important features into kind of superposition.
Less important features into the super. How does that?
In the beginning, they assign importance to each feature in this way. As we can see, as sparsity increases, the superposition measure superposition extent magnitude is increasing. Yeah, okay. As to why linear models are not able to encode superposition. The authors analyzed loss function for both linear and non-linear model, and for linear model, they come up with the next following loss. It consists of two parts, two terms. First one is the reconstruction loss, and the second is kind of interference. So linear models are not able to filter out interference, and for this reason, linear models try to set this term to 0. And this term actually defines how much the hidden vectors, hidden representations overlap with each other. So linear models just try to set it to 0, and for this reason, it encodes no superposition. If it has 5 dimensions in hidden space, it can actually represent only 5 most important features. As for nonlinear models, it is slightly different. We can see kind of a similar terms, but in this case, they have real function and bias. So if we look at this second term again, we can see that real function is 0 for so the presence of this bias allows the model to 0 the interference between hidden features if the bias is negative. So nonlinear model. For this reason, nonlinear model can learn a way to encode more features than have dimensions if it is because it is able to filter out the interference by setting an appropriate B, by learning an appropriate B bias. And the first term actually looks the same, it's feature reconstruction loss. All right.
Seems like that might be a pretty important reason for having nonlinearities in the first place.
Yeah, I guess so. All right. We found that superposition can occur, but how this superposition might look like? Before we saw this kind of superposition, it's very simple. But it can actually look like this, or it can look many ways. How do we find out what kind of superposition can occur? So the authors run another experiment for a problem with original number of dimensions 400 and hidden dimensions 30. They run the same experiment with the varying sparsity. So on this graph, we can see that depending on sparsity, the model enters different kind of superpositions, different states of superposition. In the least sparse example, each feature is represented by a single dimension, just like in the general case. As sparsity increases, the superposition states can take a different form, kind of what is it called?
Polytope.
Polytope, yeah. And as sparsity increases, these polytopes change to so. Yeah, that's superposition. An interesting question here is why are we seeing only those polytopes? It's kind of two-dimensional polytopes and sometimes three-dimensional, but we have 30 dimensions in hidden state. Why not make a 30-dimensional polytope, whatever it is? I guess the reason for that is that the bigger, the more nodes our polytope has, the bigger the interference between those nodes.
So the more, the bigger the nodes, the more the superposition.
The bigger the nodes, the more the vectors in this polytope interfere with each other. So let's consider something like that. We have a 5 hexagon. It's two-dimensional polytope with 6 nodes. It has vectors for each node, and if we see the dot product between vectors, we can see that it is non-zero. And since it is non-zero, they are positively interfering with each other, and that's the problem. But say, what if we, instead of doing 6 node polytope in 2 dimensions, what if we move to the 3 dimensions and going to like this? It's actually 5 node polytope all of that. So in 3 dimensions, we can separate polytopes. We can separate nodes into 1-dimensional diagon and 2-dimensional trigon. I guess it's hard to see from picture like that, but I think they are interfering less than this kind of polytope. Okay, so in real life, polytopes are forming like that, but they try to minimize interference. For that reason, we are mostly seeing 2-dimensional and 3-dimensional polytopes. Oh, that's good. Okay. So the authors also want to. They provide a strange reason. I don't find it very compelling that the examples we showed here. Superposition in these examples is only used for storing information in reconstructible way, but not in calculations. Okay, let's assume that's true. But now they want to consider a different problem. So they want to see how superposition affects the computations in more difficult problems, more complex problems, not just autoencode-like problem, but neural net problem. For this, they consider another problem. They want to kind of learn an absolute function, modulus function. So given some vector in n dimensions, they want to project them in given dimensions, and we can start the absolute value of the original feature vector. Again, features can be 0 is in PS, or uniformly distributed on -1 to 1. And again, features have importance. And the last function looks the same again. So this problem is nice for the reason that, okay, not mine. this. So the models that I consider is look like that. It's kind of two layer MLB. Yeah. Nice thing about this problem is that it can actually be simply solved without any superposition. If we assume that the hidden dimension is 2 times the size of original feature dimension, and we can reconstruct we can learn the absolute modulus function that way. It requires 2 times the features in the hidden space, and the weights of the learned W1 and W2 are fairly simple. They correspond to what we see here. So 1s is given this.
Could you maybe explain this again? I feel like it's pretty important, but I'm not quite getting it.
Even more.
So you have to have 2 networks to do the task that one network could do, and what, is that right? You have to have a larger network to do something. Why? Am I missing something?
Can you say it again?
Did anybody hear what it said? I don't know how to say it any other way. Could you re-explain the concept basically?
So they kind of want to approach a more difficult problem than what they had before. Before they had autoencoder line problem. In autoencoder, very simple autoencoder, the projection matrix and the reconstruction matrix is the same. It's actually just transpose matrix.
Right, so we have a latent information, so that we encode and then latent information, latent variable,
Yeah.
where you put all the where you basically put all the high dimensions into low dimension, and then you put it again, and then you transpose it again to a high dimension. That is what the decoder does, right? So in this case, the like what exactly is that the concept doing, like where exactly is the autoencoder being used in this?
In this problem, it isn't used. The previous problem can be considered the kind of autoencoder. Look at this. For linear model, it's just kind of PCA, I guess.
Linear model can't have. Oh, but wait, so superposition is used where exactly in the model is.
It's in the latent space, because there, you could think of it like, let's say you have, so the reason I use W to calculate how much overlap there is in where it's projected to is if you consider, if you go back a little bit, if you go back, if you just have an example of like the W matrix. One further. Yeah, let's say here, this one, with the -1 and the 1. So the idea is that if you get your own latent dimension, right, you have W matrix and then X here. So you get like the X is a vector like this. So every row should just contain all zeros for every column should contain all zeros, because otherwise there's other features from X that are mapped into the same latent dimension. Does that make sense? So that's why they use W to like say how much superposition there is, but the superposition itself happens in latent space. It's just that you can look at, like, if you have a linear matrix, you can just say, okay, well, these features all get projected onto this like latent vector. So in this case, it's like 2 is a latent, is a 2D latent representation. Yeah, if you go back to your W matrix, so I think that was pretty good.
This one or this one?
Yeah, this one. Back one. Yeah. So here you can see that X is 4-dimensional, right? So what happens is every row of W is multiplied by X, and then that's one, that's its late representation. So that's where you get H1 and H2, H3, H4. But you can see that let's see, that
It's basically like taking advantage of the negatives, the negative part of the space.
yeah, exactly. So you can see, yeah, it's not the column, it's the rows. So because the rows are, there's two entries on the rows. That means that two different features get mapped to the same dimension.
Mhm.
Because you can think of the row as representing that latent dimension, right? Or like what gets mapped onto that latent dimension. So, yeah, that's why they use W to look at how much superposition there is. But in essence, it's just thinking of like, okay, well, if I have a linear matrix, then I can figure out which of my features get mapped where, right? Like PCA is an example, like the components, you have like a spatial matrix that tells you where it's getting these like PCA components from, right? In the image, for example. That's essentially what they're doing. And if it's just one pixel, right? Like one pixel is so important that it gets its own PCA component. That's what they're saying where you don't have superposition. If you have multiple, then you do have superposition. Multiple get mapped to the same low dimensional space. Because if you just think of like n equals d, the matrix would just look like an I matrix, right? Like an identity matrix, because you can map every single pixel to its own latent dimension, because n equals d means that you just have the same, you can use the same basis essentially to represent the data. That makes sense. So you would just multiply it by one, like the identity matrix.
Okay.
But so also the way you can think of it is like if you go back to the other matrix, the one on the next slide, is that is not even using vector multiplication, but just the fact that like you're saying, okay, well, I minus mouth is latent dimensional one. That's what it's saying. But that only works if you assume that they're not both in the same image. So if there's an eye and a mouth, it's just going to be zero. So that you think there's nothing there.
Okay.
But you can use that to say, let's say like it's 2i, one minus one mouth, then you clearly think I is more important. And so although you share the space, I is like the main thing that's going to impact your dimension. So you're going to say, well, I is more important. So there's superposition, but you know, it's like a 45, it's like a, not 45, but it's like a, yeah, it's a 45-degree angle or something, where it's like not, the I is the most important one, and then the other one is mapped somewhere in between.
Yeah, I think if you have high sparsity, then in that case, all the features you have on just one hot feature.
Yeah, exactly.
And for this reason, we can put them into superposition in the hidden space without fear of interfering different features with each other. Each will run something.
Yeah, let's say you know only one feature is going to exist, right? You can do 2 to the power n features, right? You could just map everything to the minus of the, so you get like you need very few latent dimensions, like where n would be the number of latent dimensions. Does it make sense? But then as you increase if the sparsity like decreases, you're going to have to figure out a smart way of like not just doing it in the minus, but maybe use 2 latent dimensions that are mostly used for eye and one for tongue to find some way to fit the mouth in there so that it's shared by these 2 latent dimensions that mostly look at the tongue or the mouth.
Could you go back to the slide that you were at with had the 2 railroads? I don't think I'm good up to that point, not that one, the one with the negative X and positive X. That one. So how this point is what I'm missing. Basically, I mean, like maybe you explained it, but could you 2 in hidden neurons, you're basically so what are the 2 preludes here doing?
It's just doing the absolute function. So if you think about x being minus, it's going to be positive, right? And if x is positive, it's also going to be positive. Because if X is minus, then the second ReLU is gonna be positive, and if the other X is positive, it's positive, then only the first ReLU is gonna be. Yeah, you can write it down as like X equals minus one, like X minus, this is negative, or X is positive.
Oh, so you're effectively just finding that absolute of X, so, oh, that's,
Yeah, that's,
that's the reason you're doing that, that's the reason you're adding that non-linearity.
Well, that's why you can do it, I think is what they're trying to say here. Is like, you can use the nonlinearity to split up into two dimensions, into like one dimension into two parts, which is the negative part and the positive part. If you don't have a nonlinearity, you can't do that,
well,
right? Because it's just gonna.
on this slide, I'm actually trying to say that there, for this problem for learning the absolute function, there exists a fairly simple solution without superposition. We have enough dimensions in given state, we can do it perfectly like that.
Right, but it was the example that we're using, right, which is like the positive part of the negative part.
No, in this case, the features will be just aligned along principle. Right. So in this case, if X is just one dimensional, then the hidden state, say this neuron goes in the vertical axis and this neuron goes horizontal axis, 2 dimensions. We can perfectly understand the absolute well. Yeah, thanks. So we are learning absolute function. We know that there exists a simple solution with 2 times dimensions in the given state. What if we have less? Okay, if we take a look at the weights on this simple solution, you can see something like that. So the first matrix encodes the -6 or +6, and then tries to add to them, but we will get absolute value. In this case, say if X more than 0, then the X here will be 0. So it's not something. -6. Then we can just add them. +1 we will get yes. Yeah. Okay. What if we have less dimensions? What would then what we need to perfectly learn this function? So again, after some simulation, if for the original feature dimension, dimensional and inner dimensions, 4-dimensional, and again, assigning the importance for each feature in an exponential decaying way. They are exploring how it trains, how it behaves with different sparsity. So again, it's kind of what we seen before. In the dense regime with 0 sparsity, the model become this number is going to be 14 units of hidden dimension. So in dense regime, model learns how to reconstruct, how to find the absolute value for the 14th most important numbers. As we increase sparsity, it starts to change. So the sparsity is 0.9. We start to see that some neurons start to encode not only the most important feature like those, but also the superposition features. So it starts to find a way to utilize not only the most important neurons, but also some less important neurons, and actually minimize the loss function. The increase in sparsity. So the policy of just taking the most important features starts to gives higher loss than when the model starts to try utilizing superposition. Okay. And you can see that as sparsity increases, the number of neurons according to the superposition starts to increase.
So superposition increases for those features which are less important,
Superposition allows to encode the features about,
which are less important.
but as you can see, it happens in the sparse vision.
So it seems like that this would kind of, I mean, maybe not in this paper, I don't know, but like. Maybe it seems like at some point that there's a relationship to network capacity in this concept. Like what's the smallest network, or like how much sparsity, or how much superposition can a network handle? Or and how much sparsity before you just can't learn things.
I guess that should depend on the feature that you are extracting, right? Not on the network per se. I mean, since we are looking at the latent space and they're only storing those information, which they're only storing information about the features which are more important and less important. And for so I don't think that the number of or the network should play a lot of importance in that.
Well, I think if you have more nonlinearities, right, you could capture more complex relationships and do more complex superposition. I think that's what you could do, right? They're using a ReLU because it's really easy to do experiments on it. But like if you go deeper, right, you can have superposition in the first layer that informs superposition in the second layer, that inform right? So like, let's say you could potentially get the same reconstruction for like lower sparsity. You could get a higher reconstruction, like a better reconstruction for lower sparsity with the deeper models potentially. But it's just like harder to explain why that happens. Like in this case, we can really say, okay, these two features are superpositioning. Like if you go deeper, you're gonna have to do superposition of a superposition, which is kind of like
It's more complex.
yeah, it becomes like really hard.
And then to reconstruct it would be more painful. But then it's like you're basically just doing non-linearity on non-linearity. So it's like if you want to extract that whole feature, then it will be very difficult. But then coming back to the main point, William has a good point. Like is there any experimentation that they have done with the number of layers or like how complex networks behave in this case, or does this only depend on the complexity of the features? Or
I think they're just trying to look at what these models are doing, and to do that you have to first do the most simplest one, right? Like they're trying to make it interpretable, and the moment you go deeper it also becomes less interpretable what is actually happening. So I think the point of this was more to show, this blog post is more to show that superposition happens, and it likely also happens in even deeper layers. It's just that, you know, we know that if you go deeper, oftentimes the reconstruction of autoencoders becomes better. So clearly it's doing something more, you know, it's doing superpositions, and then finding some way to do the best superposition. But I think in this case, they're just trying to show, okay, well, with a ReLU, we at least know we can kind of know what's going on. So we can actually show you what happens when you're training it with more or less sparsity and stuff like that. But yeah, I think, I mean, they could do it with deeper networks. I think their point was more about like showing that it happens with just one ReLU, which, you know, then, you know, as you go deeper and deeper, probably kind of compounds.
no, but this is actually really interesting because as of now, I just thought like latent space is just like a magical place where you can just put all the higher dimension into lower dimension, and something will happen and then it can just go to that.
That's definitely not the case based on stuff that I've seen. It's like like an autoencoder going from high dimensional space to low dimensional space and back is, when you use just a reconstruction pixel by pixel loss, like it's always blurrier, and it seems like that's because like of lost information mapping into low dimensional space. And so it makes like the best average guess that it can do to get back to the original on the way back, but like. And the ratio of the size of the original space to the latent space is kind of predictive on how blurry it'll be.
Right.
And like if you kind of take that in the other direction, or like if you don't go very low dimensional, then you basically like get a better reconstruction. But I don't know, like anyway, that's all I have to say.
Yeah, I think latent space is a little bit of a very abstract name for something that is. You know, you can just think of it in the linear case of just PCA components generally, so.
It's also, I mean, I think that's the reason UNet has skip connections as well, but basically
Yeah.
because the lowest dimensional space is, I mean, it's just an autoencoder with skip connection in a way. And you lose information, but if you like wanna like your map from like same size space to same size space in the end, like you don't want to lose that information, so you know those connections to kind of like maintain the information that was lost throughout this lower dimensional mapping process. And a lot of applications that need much higher fidelity reconstructions will take the latent spaces from multiple layers and concatenate them together to make their final prediction.
So one question I even had about latent space is like, so I thought like all the features, like let's say you have different type of features in just one latent space, so you have different distributions, right, of those features. And then you do KL divergence on those features, and then you find out like which, and then you find out the information that you actually require. So in this case, if I look into this this block, so we are basically looking at the superposition of those features. How do I now those superpositions, given that they are in just one distribution, how do I how do I interact with the different distributions inside the latent space with the superpositions? That's something which I was more curious about, regarding this block. Like, how do we interact with different types of distributions, different type of features inside that latent space? Well,
Yeah, they do not cover it.
no, I mean, I'm just
But I guess
switching it. Even I don't
it's
know.
possible to come up with something. In this case, it is a very specific, I guess, problem. They are setting explicitly the importance of each feature, which we usually don't do in real life. Right. On the other hand, they are setting the sparsity of features the same, which is not the case in real life.
Yes.
Nice to see similar form, but with varied importance and the same spots. Yeah, so we see that model with small letter dimension becomes like it starts to be called superposition. What do the weights look like? What if we want to analyze how it is doing, how it is actually utilizing superposition? We can visualize weights, but if we just look at this, it looks kind of not really big. But let's take a look back at the weights of a simple solution. So in simple solution, we can this kind of operating sign in the first matrix and just identity in the second matrix. Let's try to decompose this into two parts. So the first part is kind of the same simple solution. Operating sign in the first matrix and identity in the second. And we can also separate different type of weights, which becomes sort of well, they're calling the symmetric superposition distribution. So basically what this does is it is learning a way to encode features can reconstruct them, but it's, small loss. They actually do an analysis of all those ways might mean. I did not quite get it. So basically, what we're trying to say is that in first matrix W1, they're contrasting asymmetrically sound difference in features, and in second they come to work with it. After we can start the regional feature inhibits the interference that happened in the same in the second matrix. It's in the first matrix. It's cryptic. But I think that's kind of all for it. One more thing I wanted to discuss is well, what can we do with superposition? Is it actually helping us? Or so there are pros and cons for it. On the good side, superposition allows us to use smaller networks. It's less memory utilization, less computations. And if we try to observe how the superposition polydopes appear, merge, disappear during the training process, we can try to make conclusions about the training. But on the negative side, it makes the interpretability of models much harder.
Yeah, there definitely needs to be, I mean, there probably is somebody that's written about this, but I certainly haven't read it. The trade-off between interpretability and like all the other needs that are sort of antagonistic to interpretability, because like interpretability people don't like anything except interpretability, but like there's other needs like compression, like just the pragmatic need to be able to store a certain amount of information in a certain amount of space, like drives, I mean, things like superposition, that seems important, sparsification, but like my interest in deep learning was a lot more on the artificial intelligence side, and just like to me, like it was acceptable to have like a black box that is able to pass the Turing test, even if you don't understand how it works. But like from an interpretability standpoint, like the most important thing is that you know how that box works and what like the limitations of any of its outputs are and stuff like this. So I don't know, it's just interesting to me that when people point out that there are other things to optimize other than just interpretability, because I hear a lot of people talk about interpretability and how deep learning is abysmal because it's not interpretable. But
I think one thing that's interesting though is that initially when we started doing those visual models, right, it actually became more interpretable what they were doing. Because when you have later layers, they would actually correspond to things that you could understand. So there's both like I think just because we go deeper and more nonlinear, right? We can get both, I think. Like if you just think about maybe not the interpretability of the function that maps to a certain representation, but the representations themselves can sometimes, like in a latent space, can be more understandable, right? Like for example, what I was doing was like mapping it to reaction time, right? That is more interpretable for us than some bold fMRI signal, right? Like it just means to us like, okay, well clearly this dimension is like corresponding to something like reaction time for people. That is more interpretable. You just need to make sure that it actually does, of course, like that it's actually picking up on something that is actually reaction time. But I think like, when you think about a lot of neuroscience research thought neural networks are so interesting because they could also help us understand like how representations go through the brain, because we could see that like if you go to layer 5 or 6 in a neural network, like a convolutional neural network, it starts to correspond to features that we can understand, like okay, does it have ears, does it have wheels, stuff like that, and that corresponds to things in parts of our brain, the IT cortex. And I think that is interesting because it's like both. I don't think deep learning per se makes things less interpretable. I just think we need to be careful to not anthropomorphize things that seem related. Like, let's say we think layer 5 corresponds to whether something has wheels, right? And that's not, we need to make sure that that's actually true instead of just, assuming that because there's a correlation that that's what it's doing. But in a way, it can also make it easier, I think. Right? Like if that's true, if it does correspond to it, does have wheels, then we can understand it. Then it really doesn't matter what happened in between. I agree with you on that. Like if there's a black box that something happens, if the output is, does it have wheels or not, and we can trust that output, that kind of makes it more interpretable because then we don't have to look at the figure or look at the image or something like that. And especially for data that we don't understand, right? Like grain data. I think it can be more interpretable as well. There's kind of this like interesting trade-off where for a lot of the time, both can't be true. And then in the perfect scenario, they can like be more than the sum of their parts. I don't know, because and it sounds like you've been talking a lot to Noah.
Yeah, like as soon as you walk up to Noah, he starts yelling about interpretability and being horrible. But I think he secretly is in love with ChatGPT without telling anyone, so. He says he talks more to it than other humans, so. All right, where's the record button?
Thank you.
I like the presentation with the
Seriously,
All right, we're done, right?
6 up.